This is the FRQ curve sketching worksheet. So we're looking at number 1 here. Let f be the function given by 3x to the fourth plus x cubed minus 21x squared. Write an equation of the line tangent to the graph at the point 2, negative 28. So if we want to find the tangent line equation, we need two pieces of information. We need order pair and we need slope. So it looks like we're given the order pair. We just need to find the slope. So to find the slope, we can go back to our equation. We can find the derivative and then evaluate the derivative at the x value. That will allow us to get the slope of the tangent line to the curve at that point. So to get to our derivative, we look at each term, and it looks like each term is prepared for us to apply power rule. So 3x to the fourth becomes 12x cubed. X cubed becomes 3x squared. Negative 21x squared becomes negative 42x. We have our derivative. We're not going to set our derivative equal to 0. We're going to evaluate the derivative at this x value 2. So if we plug 2 into the derivative, we just plug 2 in for all the x's, and all this work is shown. We get a slope of 24. So order pair is 2, negative 28. Slope is 24. And then we can write our tangent line equation in point slope form. So y minus y sub 1 is equal to m times x minus x sub 1. So y plus 28 equals 24x minus 2. All right, find the absolute minimum value of f. Show the analysis that leads to your conclusion. All right, normally if we want to find the absolute minimum if it were a closed interval, then we would go through extreme value theorem, where we test the endpoints and we test the critical point from the derivative, and we compare all those y values. But in this case, the absolute minimum for an equation that does not have endpoints means that in order for there to be an absolute minimum, it must be coming from they must come from the relative extremas. Okay, there's no endpoints to test, so the only way we can have absolute minimum on open interval is by testing just the critical points where the relative extremas are. All right, so let's find the critical points from f prime. So we have our f prime from part A. We set our derivative equal to 0. Here I can factor out the 3x, so I get 4x squared plus x minus 14. Continue factoring, I get 4x minus 7 times x plus 12. The critical points that I get by setting each part equal to 0, I get x equals 0, x equals 7/4, and x equals negative 2. And from here, we can choose values to plug into the derivative to test each interval to see what the slope behavior is. So if we plug, so here I can choose negative 3, here I can choose negative 1, here I can choose 1, here I can choose 3, right? So if we plug negative 3 into the derivative, I think it's most convenient to plug into the factored form, because all you need to do is look at the signs. We don't really care about what the exact value is. We just want to know whether it's positive or negative. So if we plug negative 3 in, this gives me negative. Negative 12 minus 7, that's also negative. Negative 3 plus 2, that's also negative. So negative times negative times negative is negative. So we know that in this interval from negative infinity to negative 2, the slope of the curve, the slope of the graph will have a negative slope. Okay, here I can plug negative 1. So negative 1 in for x, that's negative. Negative and positive. So negative times positive will give me a positive. If I plug 1 in, I get positive, negative, positive. So that gives me negative. If I plug in 3, I get positive, positive, and positive. So we know that's positive. Now we're trying to find the absolute minimum. So we know the graph is going to decrease, hits a relative min, increase, hits a relative max, decrease, hits a relative min, increase, hits continues to go to infinity. So we know the graph will look something like this, right? So looks like if the graph looks something like this, then we can expect an absolute minimum. It will have to be one of these two relative minimums. So we can test -2 and 7/4, plug both of these x values back into the original function, and compare the y values. Whichever has the lower y value must be the absolute minimum. So if we plug -2 in for the original function is given in the problem here. I didn't show the work here, but if we plug this in the calculator, we get -44. If we plug 7/4 into the original function, we get -30.816. And notice the lower of the two values is at -2, which is -44. So the absolute minimum is -44 at x equals -2. Right. And we can also may need to write out justification in words. Okay, absolute minimum must occur at either of these x values, these relative mins, since f prime is less than 0 for all of x equals -2, and f prime is greater than 0 for all of x greater than 7/4. All right, so we're given justification there. All right, part C. Find the x-coordinate of points of inflection. So if we want to find the points of inflection, we need to first find the second derivative, and then from second derivative we can find a critical point. From the critical point we can plug them onto a sine line, test each interval, make sure there's a change in signs at each of the intervals, and then confirm whether there's points of inflection. So here, second derivative, we continue with the first derivative, go through power rule. So 12x cubed becomes 36x squared, 3x squared becomes 6x, -42x becomes -42. We can factor out a 6 here, and then continue factoring. 6x plus 7, x minus 1. We set our second derivative equal to 0, find our critical points, which is -7/6 and at 1. The 6 goes away, there's no variable there, so there's no critical points. So we put our critical points, the two critical points, on a sine line. So -7/6 and 1. And then we test each of the interval. So here I can plug -2. Here I can plug in 0, here I can plug in 2. So if we plug -2 into the factor form of the second derivative, I will get -12 plus 7, which is negative, times negative, so that's positive. If I plug in 0, I get positive times negative, which is negative. If I plug in 2, I get positive and positive, which is positive. Notice that at these critical points, there are change in signs from concave up to concave down, and at 1, there's a change in signs from negative concave down to concave up, which therefore confirms that both these critical points will be points of inflections, simply because f double prime changes signs at those critical points.